Good morning, everybody. I will continue from where I left yesterday, basically on the technical options components of civil works. I think I covered basically the dam and the gravity up to gravity dam. Today, I will continue from the earthen dam, one of the types of dam, and then go ahead. Just let me go to that slide. Sorry for. Okay. Basically, in general, there are, can be gravity dams with concrete, masonry, and other materials. Also, the common types of dams in terms of cost and other features is the earth dam. And basically, earth dam are of two types. One is the what is known as the rolled fill dam, which is basically the earth material is laid over successive layers using rollers to compact them. So basically, we have, let me just spotlight this. Uh, okay, basically, the roller fill dams are rollers are used to compact, mechanically compact the layers from one layer to another. Hydraulic fill dams are placed by hydraulic methods. So they are using hydraulic machines. They are excavated, transported, and placed as hydraulic. In general, this is just the two definitions of construction. And based on um, uh, the method of construction, you have what is known as the homogeneous embankment dams. And basically, these earthen dams are composed of a single kind of material, one material, usually impervious or semi-impervious, low to moderate heights, and if they are low to moderate heights, or modified homogeneous with internal drainage system, horizontal filter drain, or rock toe. I will explain what these are in the next slides. And the other type method of construction is also zoned earth dams with more than one material, and diaphragm dams. Actually, the categorization is not basically method of construction, but it's using the materials used. I have diagrams of this, so I think it's better to explain using a diagram. So homogeneous dams are with basically one type of material. So one thing you have to be careful is you have what is in the upstream portion, this is the full supply level or the maximum water level. Okay, so there is, like we saw in the gravity dam, there is hydrostatic pressure acting on this surface of this dam. And the gravity concrete dams, they are basically impervious. So actually, there is not much seepage, okay? But whereas in an earthen dam, there is what is known as a seepage line, okay? So this has the head difference between upstream and downstream seepage line, water seepage sort of a thing, just to give you a very simple example uh, of what a seepage is. And modified homogeneous dams are, as I mentioned, used with internal drainage system. So what is known as horizontal filter drain or rock toe. So you see there is a drainage filter. So there is some slightly looser materials which will attract the seepage and it draws the seepage. So these are basically what a homogeneous dam is. Okay, and the other aspect of earthen dam is basically they have different zones. Okay, so they normally have a central impervious core. Okay, this is in the center. This is impervious, so there is seepage is very less over here. Then you have what is known as the shells, flanking of the core and more pervious. So just on the outside of this core layer, slightly pervious means there is a little bit more seepage infiltration occurs. So it's pervious. So it gives stability to the central core because there is some what is known as water pressure to the core material, and it gives stability to the central core. It also distributes the load over a larger area in the foundation. Okay, in the foundation, since then the load is distributed in a larger area, and the upstream pervious zone, okay, affords stability against rapid drawdown. So what it really means is sometimes if the water level is rapidly lowered, then if this is dry, then there is some problem of erosion on the upstream side. So since this is, there is this, the moisture content here will be relatively not as, of course, not as much as water as a volume of water, but it will not just when there is a drawdown of water, it will not just fall down. Okay, so down, and then the downstream pervious zone acts as a drain to control the line of seepage. No? The line of seepage is this seepage line, which is the 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 what you call the hydrostatic line. No, so this is the water pressure line, and then you have sometimes as a transition filter, which is basically an optional thing. A filter is basically between a pervious and an impervious layer. You have some sort of filter so that the materials don't really go from one zone to another. Then you have a drainage system. So whatever seepage, so it drains instead of really creating an uplift pressure or something. There is a drain, and which is also can also be at the toe. I mean, it can be at the toe. You have a rock toe. So this is basically the uh, the embankments with zones. And the diaphragm type embankment is a thin diaphragm of impervious material, and it is basically to provide to check the seepage, the seepage of water from the upstream to the downstream. And the material used in the diaphragm is obviously impervious, can be cement concrete or bituminous concrete. So it really creates a thinner layer. Okay, in the core, impervious core is a little bit wide and thicker, whereas the diaphragm is it's thinner. So and it really sort of it is so that because it's more impervious cement material, bituminous concrete, so it really helps to check the seepage. And there are different types. One is the central vertical core of a blanket of in the upstream side. So you can also have a core at the blanket. So there are different types that will be available. So these are the three basically homogeneous embankment type, zone, with more than one material, and specifically with a diaphragm, which is normally very impervious soil or a cement concrete, bituminous concrete. Okay, so these are, I mean, basically the three types. Now, what do we need to consider for when you design an earthen dam? So basically, one thing you have to be careful with earthen dams is it you cannot have overtopping. Okay, so earthen dams cannot overtop. So because if you overtop, then the uplift pressure will sort of destroy the dam. So you have to be careful with overtopping. Also, you have to have sufficient freeboard so that if there is like you see this is the you cannot let water overtop the dam, so you should have a sufficient freeboard. Otherwise it can create in terms of when you have a wave coming or when there is a high flow, then it can create problems of overtopping. So basic design is you have to now, the main design is the height of the dam. Okay, so you have to decide what should be the height of the dam. So to decide the height of the dam, you should know what is the high water level. Then like, and this high water level is the high flood level or water level is decided by hydrological study. So, I mean, what is the storage volume you want to maintain in that reservoir or a dam behind the dam, or it can also be if it is what will be the, when there is a high flood, what will be the water level, and now, how much should the freeboard be? Okay, the freeboard has to be, it depends on two factors. Okay, two cases. One case is when F is fetch of the wind. So when there is a wind, and in when you have a wind flowing, fetch fetch in kilometer. What fetch means is what is the on of wind blowing on the dam. What I mean to say is, like, for example, what is the, like you have an earthen dam, okay, here. Now, what is the distance from where the wind can blow here? Now, if you have a hill or a obstruction on the upstream side, then from that portion, what is the free distance of wind blowing? So what we use is, we use the two methods. One is when the fetch is less than 32 kilometer, this is the height of the wave height of that is created. And I think yesterday I like this one, from this figure, sorry, you can see you have to calculate the wave height HW, okay? And this is, this HW is calculated by using this formula when F, the fetch, is less than 32 kilometers. So when the wind is in a short distance. And if the wind is blowing from a long distance, then we use the second formula where the second, because of the fetch, when the fetch is high, the influence of these two other parameters, these are empirical parameters based on model studies and other things, then only the first parameter is important. And V is the velocity of the wind in kilometer per hour. HW is the wave height in meters between trough and crest of the wave, as I showed. So the freeboard should be 1.5 times the wave height. So I'm just giving you these conceptual design framework. Of course, when you really design an actual earthen dam, you have to look into more detail. But I think from a conceptual design perspective, I think it is important to know how these earthen dams are decided. And then the next parameter that has to be decided is the top width of the dam. So top width of the dam is normally, it should be more than 3 meters. Then we have for different conditions of when the height of the dam is very much less than 30 meter, we use this formula. When it is, less than 30 meter is this one, but very small, slow heights, 5, 10 meters, we use this one. And when it is more than 30 meter high earthen dams, the top width is calculated in this way. So these are I just wanted to provide you some of the parameters used in earthen design. Now, the other factor we have to be careful is the upstream and downstream slopes. We should make the upstream and downstream slope of the earthen dam as mild as possible, okay? But it depends on the type of soil. If there are loose soil, then it has to be, the slope has to be mild. If it is a little bit compact soil, then it can be slightly steeper. So it also depends on the foundation condition, the height of the dam. The higher the dam, the slope should be milder. And normally, from an upstream slope side, depending on the soil and the height, if it is very sandy soil, then it will be from 3 to 1, horizontal 3, vertical 1. But if it is well-graded, homogeneous soil, then it can be 2.5 to 1. So based on the based on the type of the soil, the height of the dam, the foundation condition, this is the scenario. And the other thing, there was a slight mistake. The second one, 2.1 and 2.5 to 1, is for not upstream slope, but this is for a downstream slope. And so this is, the slope is decided based on these norms, okay? And the central core, the impervious core, is designed based on the rate of seepage through the core, the type of material used, the minimum construction width, because sometimes you cannot make it more thin because there will be some construction issues, problems. And the thickness of the core should always be larger than the height of bank at the elevation at crest. So it should be, height of the bank at the elevation, and at the crest, it should be more than 3 meter, okay? So these are basically the norms used for the earthen dams, okay? And regarding the downstream drainage system, you can have different types of drainage system, what is known as the toe drain or rock toe enclosed in a filter at the downstream side. Horizontal blanket filters are horizontally placed on the base of the dam, and chimney dams are, there is a vertical layer and a pervious layer and a horizontal layer. Basically, these drainage systems are provided to basically to sort of to the seepage, to manage the seepage from the upstream side of the dam. Okay, so these are the basic design of the earthen dam. So I mean, I just provided you a very basic aspects of the earthen dam, but of course, to really design the earthen dams, you have to do some seepage analysis, which I have not covered here. But I just wanted to just introduce you to the embankment earthen dams. Okay, is there any question till now, Carlos? Because
Thank you,
from
Divas.
yeah, because I will move
Thank you,
to,
Divas.
okay.
I was just, I would like to ask my colleagues. Há alguma pergunta, por favor, nesta fase? No, Divas, you can continue, please.
Okay, yeah. So, okay. So now, I mean, this was just the introduction to the two types of dams. What is the gravity dam and the earthen dam. Now I'm going to the actual design aspects, more specific to hydropower and more specific to mini hydros. Okay, I will introduce you to some fluid mechanics concept, some hydraulic concepts that needs to be understood when you design the headworks, the intakes, and other components of a micro hydro project. Okay, and first of all, I would like to start with the headworks with a side intake. You know, I think when I presented the different layout of mini hydro projects, I showed you the headworks, and I also showed you what were the different types of intakes, side intakes, drop intakes, and other types of intakes. So here I will basically demonstrate to you the the key parts of a headwork. Okay, so this is the river, as you know. So the river is basically, as I mentioned, is flowing from up to the down by the arrow. So you are basically creating a weir because you want to divert water from the intake to the conveyance system, the canal, and the other, and to the powerhouse. Okay, from here. So in the weir, when you take a section of the weir from when you take the section of the weir from A to A, there is some echo. I hope, Carlos, you can hear me right? Okay. So this
Yes, we
is,
still can hear you, Divas.
yeah, yes,
We
please.
can hear you.
Yeah, thank you. So if you take a section of this here, the weir looks like this. So it's a raised thing of a weir, and the weir can be, I already explained earlier, it can be made of masonry, it can be made of concrete, is made of timber and other thing, but just the obstruction. But here we are talking of a more permanent wear. Okay, and uh, and so what? So this is the basically, if you take a section, this is the wear. The crest of the wear is raised so that the water level is raised in the upstream side. In the wear, actually especially for slightly larger hydropower projects, the wear consists of two sections. Is what is known as the sluice here, and the other is the wear like this. The sluice portion is the level, like the level of the sluice portion over here. here, this is the crest height, but undersluice is slightly depressed. Okay, it is the level here of the undersluice is slightly lower than the main weir, and there is a divide wall in between the main section of the weir and the undersluice. And the reason you provide the undersluice is because you want to, I mean, sort of direct the water towards the intake. Because if the level of the weir on from across the river is of the same height level, then the water will just flow in a straight manner. But you want to sort of divert it towards the intake. So this level of the undersluice is slightly lower. It also, the undersluice can be gated. You know, you have a gate in the undersluice, and this can be used to flush the sediment that is deposited upstream of the intake area, in the area that I am showing it here. Okay, so you have basically an undersluice. It can be a gated under, it needs to be gated because you want to maintain the water level up to the normal water level. So it has a gate, but you operate the gate so that any any sediment, sand, and other gravel, even logs, everything can be flushed down easily. Okay, so this is the purpose of the undersluice. And here on just before the intake is, it's a side intake. So if you take a section from B to B, looking this side, okay, this is the section B to B. If you look from this side to here, you can see that this is the side, this one is the trash rack. So trash rack is basically, there's a steel or material. This is small holes with some spacing. So this trash rack will protect logs and large sediments, you know, boulders, everything will not enter into the intake, okay, from here. Okay, so this is the trash rack you see here, and this is the undersluice here. Okay, this one here is undersluice, and this is gated. You see, the undersluice bed level is at the, sorry, the undersluice invert level is at the bed level. When you do a B by B section here, this is the undersluice. So this is the trash track. Then behind the trash track is, of course, your intake, which I will talk about later. Okay, so this is just the diagram of the headworks. Similarly, I also want to show you a headwork with a bottom rack intake. This was with a side intake. Okay, on the side you have trash rack, and just behind the trash rack you have the intake, side intake. Whereas in a bottom rack intake, what you have here is on the weir itself. Okay, on the weir inside here itself, it's in the other side. The intake is in this previous one. It was on the left side of the river. In this case, it's on the right side, but it could be on either side. So this weir has here a bottom intake. So over here, this one is the trash rack over here. Okay, so if you do a section from the on the side of the bottom intake, this is the section. So you have a weir and you have a trash rack here, and water actually basically whatever, when the water comes on top of the weir, on tops of the trash rack, then it drops, the water drops to this intake, and from the intake it goes to the waterway. So the intake is something, this is the intake detail is given here. Okay, so there is, this is the, it's a bottom intake. So water rail actually vertically falls down to the intake, and this side is, of course, the section on BB is the weir section. Okay, so part of it has the intake. So these are the two types. There are other types of intakes also, But these are the two types of intakes I just wanted to introduce to you. And based on that, I will now start the design of the weir. Okay. So when you design the weir, okay, this is the weir. Now, what should be the how much of water flow can pass in the weir is a hydraulic calculation. You have to use is a formula to calculate that. And basically, this formula is very simple. It's a fluid mechanics formula, which is basically discharge of from overflowing the weir is equal to a coefficient CW. CW coefficient I'll explain, and the length of the weir. From length means from one bank to the other of the river, and the overtopping height. Okay, the overtopping height. That means the head over the crest and the flood level. Suppose you have to pass, let's say, 10 cubic meter per second of discharge, okay, in the from this weir. Now you want to know what would be the water level, high flood level for 10 cubic meter. So that one, so your Q is 10 cubic meter per second, okay? And so you want to know the H top, okay? So H top, sorry, H over top. So H over top is what is the height of the water above the crest level. So H will be, what will be thing will be Q divided by CW and L where. And let us assume L, let's say 10 meter, okay? If L is 10 meter, what, and the discharge is 10 cubic meter per second, and what will be the height of the water level above the crest? Now, this weir coefficient will depend on the shape of this weir. Okay, if you have a broad crested weir, it will be 1. Broad crested weir means you have something like this. Okay, so it's 1.5. So the so basically the height will be very small in this case. Okay, because the H is equal to Q divided by CW times L. Okay, so basically based on that, you know what will be the how much when discharge when flow in the river, when you create an obstruction, okay, what will be the height of the water above the crest level is found in this way. Okay, this is a very simple formula, but very useful, okay, to in a weir design. Because the reason I say this is because if there is a flood, and if the high level is very high, in the weir, if the weir cannot control the pass the flood properly, then this flood will spill over bank and it will go over the bank. So this is a very simple formula, but very useful to in designing the weir. Okay, so so this is just just the introduction. We will come back to this when you do the exercise, but I wanted to introduce you to that. And after that, you have to now plan for a design of the side intake. Okay, and this side intake, okay, so you have from here, sorry, okay, from here, this is the side intake. Okay, so I just show it here. So you have the side intake on this side. This is the under sluice here. So you have basically the trash track here, and then it goes to the side intake. Now, some of the design consideration, the important thing you have to consider when you design a side intake is that you have to uh, uh, make sure that there is the side intake, the water level above the intake. Okay, this is on the, if you see the front view, then the normal water level. Okay, the normal water level should be higher than the top of this intake. Okay, at least it should be 30 to 50 centimeter even in the dry season, because if it is half, then it will not meet your water requirement. Okay, so the invert level should be, the invert level is the bottom level of the intake. It should be zero 0.5 to 2 meter above the undersluice level. Okay, the level here, so it has to be more than this. And the capacity, it should be 10 to 20% more than the design flood, no? Because we will use it for flushing requirements. I think yesterday or day before, there was a question about how often should the gravel trap be flushed. It is basically, and I will come to the gravel track design also. So I think I have it here. I will explain that in more detail. It is basically a continuous process. So you have to, so some part of it, of the water that goes to the intake is used for flushing. That's why the capacity of the intake is 10 or 20% more than the design flood, sorry, design flow. The entrance velocity, what should be the velocity of the entrance in the side intake? It should be around 0.6 to zero 0.8. It should not be very high. No? And for small system, you could have up to 1 meter per second. But normally it is between 0.6 to 0.8. Okay. And on the outside, you provide coarse trash track to prevent big boulders and the floating log, which will just stay here and it will pass through the undersluice gates. The gate stop log may be provided to regulate flow. The intake can have a gate or a stop log also. And there will be a spillway provided close to the intake. So these are some basic design concepts that are followed when you design the intake. Okay. And now watch, because one thing as you must have noticed is whenever you design the waterway for the mini hydro project or any hydropower project, you try to minimize the losses, because any loss means the head will decrease. The head available for power generation will be reduced. So you have to calculate, no? That's why you have gross head and you have net head. The difference between gross head and net head is all the losses that occur in the process of water from the river to the powerhouse. So one important factor for design of a side intake and orifice design of a side intake is what is the head loss, the intake head loss calculated. And basically, it is calculated using a formula like this. And normally, V square by TZ is basically the velocity head. So part of that velocity head, okay, is lost due to the contraction, the shape, the angle of the intake. When the water flows from a larger area to a smaller area, or from a smaller area to the larger area, when there is contraction, when there is transition, then there is a loss, a frictional loss of head. So the formula used is the intake loss is HFI head loss is equal to K times Vn square divided by 2Z. And Vn is the normal velocity in meter per second. K is the intake loss coefficient. And intake loss coefficient consists of two factors. One is the due to the intake loss coefficient due to sudden contraction in flow from the inlet pond as it passes the trash racks and piers. So again, when you have a sharp crested shape of the intake, a bell-mouthed shape or a slightly rounded shape, then you have the various coefficients of losses. And KT is the gradual contraction losses as the flow follows the transition part of the intake to the intake gate. So depending on the angle, okay, from the intake to the intake gate, the KT also varies. So based on that, based on these intake loss coefficient, you basically find the intake head loss. Okay, so this is a formula that is used to calculate the intake head loss. Okay, now the other factor when you design your site intake is important. It will be what should be the size of this intake opening. Okay, because the intake is normally you have certain opening orifice, no, a hole. So the H is the height of this orifice, the intake, and B is the width of this orifice. So now what should be B and H? So orifice is an opening in the intake for which the river water is conveyed, from which the river water is conveyed towards the headrest canal, so towards the canal here. Now, the velocity of flow entering this hole or an orifice is given by a formula. Again, it is given by C under root 2G and the head difference in the upstream and the downstream part of the intake. Okay, so this is the normal water level. This is the water level at the river next to the orifice HR, and the H, I think I call it water, the same datum, and this is the downstream in the headrest canal. So there is a, actually it should be HH, HR and HH. This should be HH. So there's a small spelling mistake here. So based on this, so what it done? So difference, this is H1, HR minus HH times 2G, square root of that multiplied by C, the coefficient of discharge of the orifice. And again, this C is depends on if it's a sharp edge, roughly finished concrete masonry, it is 0.6. For carefully finished, it is 0.8. And the area is, so Q is area, A is the area times V. So this is the reason why you have key. So once you know the discharge through the orifice, okay, so you need, so you will get how much of discharge can pass through this orifice. So you, if you need, suppose you have to, like for Majau, the design discharge was, let's say, 4.5 cubic meter per second, but now you want to give at least 20% more, 10 or 20% more. So if you design the intake for 5 cubic meter per second, then you can find the size of this intake orifice. And this is the formula used to design the intake orifice. Okay, so this is the design for the intake orifice. Now, so what the design of the site trash tracks for the site intake is done based on a certain velocity profile. Okay, And it is, as I mentioned, manufactured using steel plate, angles, tees, or round bars. Okay, it's just steel bars that are used to design the trash rack. And the clear spacing of this trash rack, okay, the spacing of this trash rack is between 55 millimeter to 200 millimeter, so that any small logs or sediment or small gravels, rocks larger than this side doesn't enter the trash tracks. And the approach velocity, because you should not have very high velocity approach. So it should be 0.6 to 1.5, okay? Because if you have very high velocity, it can also take damage, it can erode the, what you call the canal and the orifice materials, okay? And the surface area of the submerged part of the screen, it has to be, this is the formula that is used to calculate. So based on the rated discharge, how much of, I said, if you want to pass 5 cubic, 5 cubic meter per second of discharge, and depending on the bar width, okay, what is the size of the bar and the spacing of the bar and the coefficient K1, which is related to partial clogging of the screen. So if there is no automatic raking, if you have to do manually, then we assume 0.2 to 0.3. But if there is every hourly there is an automatic raking, then it's 0.4 to 0.6. And if there is a differential pressure, means when there is when the trash track is clogged, then you have some differences from the upstream and downstream. Then if it's an automatic raker, then you use a value of 0.8 and 0.5. And the angle of the screen, angle of screen with the horizontal is alpha. So basically, you calculate the submerged area of the submerged part of the screen using this formula. So basically, you want to get the screen, the trash track, like trash track, you see, this is the submerged part. So you have to make sure this area is available for the water to pass here. So if you want to design for 5 cubic meter per second, then you have to design the trash track accordingly. So it will be normal water level. For flood level, of course, it can pass more, but you basically design for a normal water level. Okay, so that is the design of the trash track. Okay, and there is a head loss from the trash track also. So you have to calculate. Originally, we calculated the head loss from the intake. Now we calculate the head loss from the trash track, and we use a similar formula. This is the velocity head, but then we use these coefficients of K T over A to the power 4/3 sine alpha, and T is the thickness of the rack bars, A is the spacing of the rack bars, V is the velocity of the trash tracks, and the angle of bar and the K factor depend on the shape of the bar shapes. Okay, so this is how we calculate the head loss from the trash track. I want to start gravel trap next, but I think it will take longer than 5 minutes. So I want to put some questions just to make you understand. Okay, on the where. Okay, I want just like to highlight this where. Like I said, the weir has to be designed in a way that the flood passes over the weir without causing any overflow of the overbanks. So the main purpose of this weir design is to find what will be the overtop height. Okay, what will be the height, what will be the high flood level. Okay, so earlier I was giving, and normally 10 cubic meter per second is a very small value. So let's say, I mean, if you go for it, if it is 100 cubic meter per second, okay, is the flood Q value, and L is is, as I said, 10 meter wide, and you have a broad crested where CW is 1.5 meter. So, okay. And so what will be the head? So what will be the head if this value? So I will just just to give you an example. Okay, I want to like do a small exercise here. So flood, can you see my, I will make it a little bigger. You can see my screen, right?
Yes, we can see it.
Okay, let me just I'll go to my mouse. Okay, okay, I will do again. So Q is, the flood Q is, let's say, 100 cubic meter per second, okay? The length of the weir is 10.
Hello, hello, Divas. Hello, Divas.
Yes, please.
Hello, Divas.
Hello.
You may probably select a bigger font.
Okay.
Or you expand it. Too small. You see, from far.
Okay, I'm just making it bigger. Okay, just a moment. Okay, let me just select a bigger one. Okay, now you can see.
Oh, yes, now it's okay.
Okay, so you have a river cross section, which is 10 meter. You want to pass discharge of 100 meter, and your CW is, I use 1.5 because it is okay. 1.5 is for broad crested weir. Okay, so based on that, so now what will be the H? Okay, is important. Okay, now what will be the head over the river channel? Okay, okay, this is the question mark. Okay, okay, so we need, because we need to know, we need to know, you need to know the H over here, you see. So what I do now is, so we use this, you use this formula, Q is equal to C times L times H to the power 1.5, okay. So now if I use this formula here, so this will be Q, sorry, Q is here, Q divided, sorry, what did I do? Q divided by, okay, 1.5. Sorry, let's just put this formula here also. This times Q divided by 1.5 to the divided multiplied by L, okay, and this one to the power, it's 2 by 3. Oh, I made some mistake in the, yeah. So you see the, I hope I did not make. Okay, so the head will be 3.5 meter. So what I mean to say is this H will be 3.5 meter above the crest level. And the reason this calculation is important is, if the high flood level, if this level is more than the river bank, the water will flow to the banks and it will create flooding. Okay, so you have to make sure the weir is the water level above the weir is not higher than the river bank, and it helps you design this. And if it is higher, then what we have to do is we have to change. Instead of using a broad crested, maybe we have to use a more rounded, okay, more round type of shape, because this will increase the coefficient 2.2, so it can pass more discharge for the same length. Or we have to increase the length of the weir, and the length of the weir is sometimes restricted by the river channel also. So you may have to sort of increase the bank width to be able to pass this discharge over here. Otherwise, you have to have, if you want to pass 100 meter per second, it would be 3.5. And if the flood, let's say, is 500 meter, okay, then the head will increase to 10. Okay, so you have to be, you see, if it is 100 cubic meter per second, it is 3.5. But if it is 500 cubic meter per second, it is 10 meter. And so what it shows is, if the bank height here is, let's say, 5 or 6 meter above the crest level, then this river cannot pass a 500 meter per second flood without flooding the banks. Okay, so, and this can create problem. So hydropower design needs to also consider such a condition. Okay, so this is basically something that I wanted to point out. Okay, and similarly, of course, there are, and we will do some practice, you know, like in the exercise during the feasibility in the maybe in December or January, we will have exercises of real projects where we will design, I mean, do a study and analysis exercise on design of weir and side intakes and other components of hydropower projects. I think